Nice to meet you. Let me invite Mr. Professor Dionisio from University of Portugal. I'm sorry for the right name of university, but
Castelo Branco.
Castelo Branco, okay. And he will present for us for about 60 minutes a very interesting tool which name is SEAMCAT. SEAMCAT, I think.
Yes.
Spectrum Engineering Advanced Monte Carlo Analysis Tool. And we will do also some practices with him. So be prepared, we will use the computers. I think it will be useful.
Yes,
It's
yes,
yours.
okay. Well, thank you. So, first of all, thank you for letting me be here and present this tool. So, my name is Rogério, I'm from Castelo Branco, as they told me already. Castelo Branco is a middle-sized city in Portugal, about 50,000 inhabitants. And we are not far from Spain, probably about 50 kilometers. And approximately 300 kilometers from Lisbon and 300 kilometers from Porto. Okay. So we receive every year around 200 students, incoming students, Erasmus. And right now I also have a few students here studying at the Faculty of Electrical Engineering. Probably you know them. One is Diogo and the other is Ivan. So, okay, so getting back to SEAMCAT. So SEAMCAT is a tool for analysis of interferences, okay, mostly interferences. So, keep the first one. So this is more or less a summary of the presentation. So don't worry, I will be quite brief on this presentation, maybe 10 minutes, and then the remainder of the class will be practical. Okay. So I think you will all have access to a shared folder. On the shared folder you have some exercises and the guide also to the exercises. Okay, but we'll get to that later. So first of all we'll present SEAMCAT. So why SEAMCAT and what is SEAMCAT? Some of the terminology that we use in this tool, and then I will show you here how to use SEAMCAT in 5 minutes. Okay, and then we'll start with the exercise. So, first of all, why do we use SEAMCAT? Well, because the spectrum is crowded. And that's what we do now. Most of the spectrum is full with application, radio application from many industries, mobile operators, DVB-T broadcasters, and so on. And the number of applications is increasing every day. Okay? So this is a huge problem for national regulators and worldwide regulators of the spectrum. Every 5 years, I think they are gathering together and then decide what will be used in which frequencies. And sometimes they have a lot of confrontation because some countries are using different frequencies. Okay, so mainly in the borders, this can be a big problem. So. But anyway, so SEAMCAT is a tool developed by the one group from the European Commission called the STG, and the tool started to be developed about 15 years ago, and it continues to be developed. Okay. So with SEAMCAT, we can obviously do sharing and compatibility studies between radio systems. This is the main objective of the SEAMCAT tool. Okay. So this tool is open source, so it was programmed in Java. Okay. This is why you need the JDK platform in order to run SEAMCAT. But SEAMCAT then can run in any operating system, Mac, Windows, Linux, Raspberry, if you want it. Okay. It will run in every platform. It's free, so you can download it at any time. And it is essentially based on the technique called Monte Carlo simulation. Okay. So this is more or less, in a nutshell, statistical modeling of the radio systems. Okay. So in SEAMCAT we don't need to define the modulation type for any kind of system, but we have to define a lot of parameters from the transmitter, receiver, propagation model, distances, mobility, so it has to be defined on the first hand. This is probably the most difficult part of the software. Okay. And at the end, it will give you just one result, which is the probability that this system will interfere with this one. Okay. And probably for most of the regulators and national regulators, this is what is most important. Those systems will interfere with each other, yes or no? How much? Okay. So, I can tell you that the last study that I was following was between LTE on the 800 MHz band and DVB-T broadcast systems that also around the 700 MHz. Okay, so in some places they were interfering with each other. So they made a lot of studies with SEAMCAT in order to understand why was this happening. Okay. So this is the symbol of SEAMCAT. So this is a tool from the ECO, and as I told you, it's here since 2005, I think. So SEAMCAT is intended for coexistence studies between radio communication systems operating on the same or adjacent frequency bands. Most of the systems are operating, and we can simulate systems mainly under terrestrial services, but we can also define scenarios involving satellite systems, okay, fixed links. The software will give you a probability of interference, so which is actually a number, okay, and it means that this is the probability that one system is interfered by one or more other systems. And SEAMCAT is not designed for network planning. Okay, so if you want to do network planning, you will use another tool, but not SEAMCAT. Okay. Any questions until now? Okay, so first we'll talk here about terminology. So probably the most interesting here are this figure here. So we have here four towers. Each tower will have an antenna and a radio system. And in SEAMCAT we have essentially two kinds of systems. One we call the victim link, and the other will be the interfering link. Okay. Each link has a transmitter and a receiver. Okay, and each system has to be defined correctly. Okay. So, the victim system in that case is this one. The transmitter is here, the receiver is here. The interfering system is this one, and the problem will be caused by this transmitter interfering into this receiver. Okay? So we have mainly here two important signals. One that we call the wanted signal, which is the signal that transports the information that we want to receive, and the other signal will be caused by this transmitter, and we call it the interfering signal, that will be also received here. Okay? So we will be receiving two different signals. One we want it, the other we do not want it. Okay? Okay, so following. So this is more or less the terminology that we are going to use. From the victim link we have the victim link transmitter that we call VLT. The victim link receiver VLR. Then those terminology will be on SEAMCAT, so you need to understand it. And finally we'll have here the interfering link transmitter, this device here, and finally the interfering link receiver, which is here. Actually this receiver is not important for the interference studies, but it has to be defined and positioned correctly, because it will define how much this signal will be on this direction. For example, if we are using here directed antennas, okay, we need to define that the right direction of the antenna from this transmitter is this way, but we also have some lobes, energy lobes, that will be propagating signal in this direction. So this is why it is also important to define this interfering receiver, to point the antenna on the right direction. Okay? So this will be the basis of the first exercise. All systems are fixed. There are one interfering link and one receiving wanted link, and they will have more or less this position. Okay, so for SEAMCAT, so this is already the interface that we will see on the exercise. So first you have to open, or you have to create a workspace. Okay. So if you already have a workspace defined, then you just have to open it as usual. So there is nothing new actually here. The interface is quite common. You can open the workspace. So the files from SEAMCAT are called with an extension SWS. Okay. So you have two SWS files on the shared folder. One is exercise 1 and the other is exercise 2. Okay. We'll start with the first one. And when you open the workspace, you will have this tab. This is the name of the workspace, and inside this tab, 3 more tabs. One called Systems, one called Scenario, and one called Event Processing. This is true for every workspace. Okay? We'll go through these 3 tabs now. So, the system is where you set the properties of the systems to investigate, power, antennas, height of the systems, so everything has to be defined here. Okay. On the receiver side, you also have to define the noise level if you want. The bandwidth can be also defined here. Then we have the scenario, and the scenario will set how the systems are far from each other, and which propagation model will be used between them. Okay. The scenario will also set the scenario between the systems for the victim and the interfering link. And finally, the event processing can be used to see intermediate results for the simulation process. Okay. What can be simulated in SEAMCAT? Essentially, it's divided into 2 groups. One is called generic systems, and the other one are cellular systems. So we can simulate both. On the generic systems, land mobile, short-range devices, point-to-point links. Some of the examples are here. For example, a satellite system link can also be simulated here. On the other side, we can also simulate CDMA and OFDMA systems, cellular systems. Okay. So here, the position, the location of the antenna is defined through an hexagon sheet, as usually we use that for cellular systems, and the interference is computed using this approach. I will not present these today because for that I need a lot of time. So I will keep the presentation and the exercise on this side. Okay, going back to the parameterization of the systems. So if you click here on the tab System, you will have 3 more tabs called Receiver, where you define all the characteristics of the receiver, sensitivity, bandwidth, antenna, blocking response, interference criteria, and so on and so on. Did you already talk about this in other classes?
Yeah.
What is an antenna? You have a lot of antennas here. Okay.
Who is expert in antenna? Where is Mike?
Okay. So here on the receiver and on the transmitter, you have to define all the properties. Power, antennas, and so on. Then you have to define here the path between the transmitter and the receiver. SEAMCAT has already maybe 20 propagation models defined here, from ITU and other organizations. And by the way, free space is also there. Okay? Free space password, the simplest one is also here. Okay? So this is for the systems. So the systems actually are transmitter, receiver, and path between them. I will skip this one. This is on CDMA or FDMA. Then we have the second tab, which is called Scenario. And on the scenario, we will define where is located the interfering system and where is located the victim system and the interfering system. They are moving, they are not moving, they are fixed or not fixed, what is the propagation model between them, so it can be defined also here. Okay. Have you heard about Okumurata?
About?
Okumurata model?
Yeah,
Yes.
yeah.
Free space path loss model. So they are all here and among many others. Okay. So this has to be defined here on the scenario side. So it will define how the interfering signal will go from this transmitter into this receiver from the victim side. Okay. Finally, after configuring everything, you can check with this button here if everything is okay. So this is the first step. If you didn't mess on the parameters, okay, it can be checked here. So before going into simulation, you should check if the consistency of the system is okay. And finally, we select the number of events we want to simulate. I will say, by default, these are 20,000 points that will be simulated. Don't forget, this is a Monte Carlo simulation, so you need a lot of points. The more points, the better. Okay? It will depend on the machine you have in front of you. Okay? Usually with 20,000 points, for example, on my Mac, it takes 2 seconds. Okay? If you want more points or more simulations, you have to take care. I heard you have a super computer here on Ostrava, so it will be nice to use it also with that. And finally, you run the simulation with this button, and after that, there is another tab that is created called Results. Okay? And on the results, we can see 3 other tabs: the outline, the results, and the interference calculation. So I will go through all of these. So these workspace results can be saved, so you can save the results for later analysis. On the outline, you will see the simulation outline. Let's say all the parameters that you have defined. It will be listed. You can copy to a text file for later use also. Here the list of all the results. Most of the results are vectors, so you will see vectors points. Okay. And finally here on the interference calculation, this is where we will actually compute the interference between both systems. And at the end we have one result. So everything just for one value. Okay. Okay, this is just an image of the outline. So here on the outline you have, for example, the location of the transmitters, receivers from both systems. In that case, I should say they were mobile, because we have scattered points here, so they are all mobile. And here we have a statistic, let's say, the signal by itself through the time. So you can see both the desired and the interference signal. Okay. Here on the results, inside the results, so this results tab, here we have the outline of the simulation, and here we have all the vectors that were defined here. And we have also this on the statistic of the simulation process. For example, in that case they were using a quad-core processor. It can be seen here. The time the simulation took, about 0.09 seconds, and the simulation date and so on. Finally, this is the last picture. Here we can see on the interference calculation. First we define which kind of criteria we are going to use for the interference. Here it's carrier over interference. But it can be also carrier over noise plus interference, and so on. So it depends on the kind of criteria you want to define. For example, if you define a C over I of 10 dBs, this is the minimum C over I that you have on the receiver side, acceptable. So below that value, you can consider you are going to have interference. This will happen 20,000 times if you have 20,000 points. Okay. There are 2 types. Compatibility will give us one result. Just one value of interference probability. In that case, for example, 0.70, which means 70.5%, okay, of interference probability. But we also have another mode called translation, when we can compute the probability of interference as a function of predefined parameter. For example, the power of the interfering transmitter. We can increase it or decrease it along a scale, for example from 0 to 100 dBm, and then we will see the probability of interference increasing or decreasing. This is interesting when we want to know, okay, but I have this value here, but what if I decrease the power of the interferer? What will be the interference? So I can change it and check exactly what should be the power. Okay. Okay. These are also some results of the simulation. We have here a probability density function, here the cumulative density function of the vectors, and here the signal that was generated. I always tell my students this is a good example of probability and statistics courses that must be applied here. You have to know exactly what is there. Okay, if you want more information about SEAMCAT, you have online handbook. This handbook is more or less outdated because it's from 2015. So a lot of things have happened since then. But the wiki is always updated. So usually it's preferable to use the wiki because it's actually the same as the handbook, but better. So now let's go to the exercises. How long do I have?
Yeah.
Half an hour maybe?
40 minutes.
40 minutes.
40 minutes, okay. So I have here already SEAMCAT.
Yeah, turn on the computers and you have the shared folder which you can find.
Wait, of course.
If you list, there is a shared folder which is EB209. If you have disks, yeah, there is a shared folder. Follow my screen. EB209. Sure.
Everybody seeing this shared disk?
It's the shared disk, yeah. Can you see them? Yeah. There is a very strange name of directory. Student Zapis. Yeah. Yes, student Zapis. And inside them you can find the SEAMCAT. Run them. Yeah. Directly double click here. SEAMCAT.
You can click on SEAMCAT.
Yeah, SEAMCAT.
5.0.
Yeah. And then
it will open the program. Okay.
Follow the instruction of professor. Excellent.
Okay, so everybody is here in this image site. So by the way, you can see on the here this is the symbol of also the institution CEPT. CEPT is actually a European institution that, let's say, more or less guides the national regulators about what to do with the spectrum.
I thought that CEPT was moved or converted to ETSI, but it's not true.
No, ETSI is
more or less
it produces standards for CEPT.
Okay.
Okay. So ETSI is more on the standard side. They produce standards. That's it. They don't define what we should do with the spectrum.
And ITU is
for ITU is
the highest.
Yes. So ITU and CPT will tell ETSI, okay, we'll use this spectrum to do 5G.
The ITU is worldwide and CPT is only for Europe?
It's for Europe. And you have other organizations in Japan, in United States, South America. And ETSI will check this and will define standards for these technologies and spectrum bands. Okay, so you can click on the open. If you are already the open, you have on the folder classes you have two examples. You just have to click on the first one. Exercise 4.
The same folder, the same
folder as previously on the shared disk. Okay, you have to go to the shared disk and then a folder called classes and then click on it. Everybody found the exercise? Yes, no, maybe?
In which folder?
It's EB10.
EB209.
EV209 as the student service, and then you have
example.
two SWS files, one and two.
Here.
So you just have to click on the
And the
first one.
same. Great.
Okay?
Great.
First one.
Yeah, great. This one. Double click. And first one. Great. Run this, yeah. Directly.
Okay. So in that case, everything is already prepared. You don't have to predefine any kind of parameters that because they're already here. Anyway, you have also on the shared folder a guide to define the parameters. Okay, so later if you want to try by yourself, you just have to pick the guide, pick SEAMCAT and start putting values. Okay? So I will go through this. So here you have this tab called 5 ESP exercise 1. Okay, this is our exercise, and you have here three tabs: systems. Then you can click here on scenario, and finally you have here the event processing. Okay, this should be completely empty because we didn't have any simulation for the moment. And we'll go back to the systems. So here on the system you have here two systems already defined, the victim link, and if you click here you can see the properties of the interfering link. Actually they are exactly the same. Okay? Same frequency, same everything, so they will interfere for sure because they are using the same frequency, the same bandwidth, and they are not far from each other. Okay? So, just to check here the victim link, what we have here. Okay. So we have here on the right side the default frequency. Right now it's 1000 megahertz. Okay. So you have here 1000 megahertz here. If I click here, definition, I think I have to click twice, right? I don't know what is not opening. It open for you?
Yeah.
Okay, whatever. So okay, on the distribution, if you are, I'm not looking, but okay, you can define a constant frequency, uniform density, so varying between two values. So we can define a lot of ways how to define frequency of signal. Okay. For example, if you have a Bluetooth systems, you know that the Bluetooth the frequency is hopping from 50 or more channels a lot of times. Okay, so you can define these specific channels. So instead of using one frequency, you can define a lot of frequencies. For that, you need to define a stair probability, stair cumulative probability. So I will tell you how to do that.
Some delay.
It's short. I will cancel it. Okay, here on the receiver you have the receiver ID. Here you have the height of the antennas, the elevation. You can define the azimuth and elevation. Here on this window here, I will open a little bit to see everything. You can define the antenna peak gain, and if you want, you can define the horizontal and vertical patterns. For the moment, they are not checked, which means that the antenna is omnidirectional, horizontally, vertical. Okay. SEAMCAT gives you a library. By the way, I will go here, library. You can click on library, and we can go to antenna. Where is the antenna gain plugins? Maybe this one. Okay, I will pick this one. Hope it will open. Okay. So here are all the antennas that are already predefined, and you can use on SEAMCAT. Obviously, you can import whatever antenna diagram you want. Okay, but that way we are going to check one of them. For example, this ITU RF here. So there is a short description what you can do with this one. We'll try to see the diagram, show gain plot, clicking here. Okay, we will see this on the polar here, vertical polar. This is the polar diagram of this antenna. You can see it on the spherical. Okay, so we have several types of antennas here that are defined, and you can select whatever is useful for your simulation. Okay. Okay. I will cancel it. You also have a library with several other parameters for receiver transmitters that are already predefined. If you want, you can also create an element for the library. If you are simulating something, you can create all the parameters and save it as a library parameter. Okay, for example, another antenna if you want. Okay, so on the falling back on the systems, we have the receiver, we have here the transmitter tab with the parameters of the transmitter. By the way, the power here is constant, 30 dBm. On the following tab, we have the transmitter to receiver path. I will start from this right side. Here we can choose the propagation model. What is the propagation model right now?
Free space.
Free space. Okay, so
No obstacles, no objects.
no obstacles, no objects,
Only.
nothing between transmitter and receiver.
Mhm.
But if you want, you could change this by using this button, I think, input, yes. So these are the propagation models that you can use. You have the extended ATA, short range devices, ITU, P452, 14, 15, you have the free space. You have a lot of models here. Some of them can be already used for 5G communication. Okay, but I will skip it, I will stay in the free space. Okay. If you want, obviously, the program in Java, you can program a propagation model, create it as a plugin, and then put it here. Okay? So it's up to you. Finally, here we have a button called variations, and it is used to include noise on the signal with the 1 dB standard deviation. Okay? We have to do that here because the systems will not move between them. So if they are not moving, if we are not inserting noise, the signal will be always the same. Okay? But in that case, I will insert some variation on the signal, which is mostly thermal noise on the systems. Okay. Okay, following here on the system layout. So here, this window will show you how the systems are positioned between them. This is not quite really a nice interface, but because we cannot see everything. But anyway, you have here the transmitter and here the receiver. Unfortunately, here we have the scale 1 kilometer, but this is not quite nice, I think. They have to improve this. Okay. On the interfering link, there is something quite similar, so I will skip it and I will go directly to the scenario. Okay? So clicking on the scenario. Here on the scenario, we have to define which system will be a victim, so because we can choose anything we want from the ones that are already created. The frequency, here on the right side we will define the number of simulation points, and here we can run the simulation and here check the consistency. I will already check if everything is okay, so you can click on the print button with and check if everything is okay. Everybody has this kind of message? Good. Okay, and finally here the relative positioning. Okay, this is very important because here you will define how both systems are positioned between them. In that situation they are correlated, which means they are fixed between them. Okay? No mobility between systems. But you could define, for example, if you want, uniform, and in the uniform you can define a cycle when the systems can be moving, and you can also define the position inside this cycle, where one system is corresponding to the other. But I will skip that. So both systems will be correlated. I will open a little bit the window with delta x 4 kilometers and delta y to minus 2 kilometers. So one system will be here, the other will be more or less here. Okay, fixed. No mobility between them. Okay, doing this, we'll start the simulation. So you can click on this button here on the start event generator and wait a little bit. You have the results already? Okay, something is appearing already. Okay, so that's it. Okay. Well, explaining you what we have on this scenario outline are actually 4 points. Can you see the 4 points? Here you have 1 point, here another one, and here below you can see another one. And finally here on the origin there is also a point. It's almost invisible, but it's here. I think we can zoom out or zoom in. I think we can do this. Can you help me on the zoom out or zoom in? Or zoom out?
Privilegied is zoom out. Zoom in. Zoom in.
Zoom in. Here?
Without it.
Yeah.
I will try.
Yeah.
Okay, actually I want to do a zoom out.
Mm-hmm.
Zoom out. Okay, now I can see the 4 points. Okay. So you can see the legend here. So here we have a victim link transmitter, and here we have the victim link receiver. Exactly. So this is the victim link here, and here we have the interfering link. So from this one to this one we'll have the signal we want, the desired signal, and from this transmitter here into this receiver the interfering signal. Okay. And the interference will be computed between these two signals coming into this receiver here. Here you can see some statistics of the signals in dBm. Here we have the desired signal, DRSS. And here SEAMCAT divided the interfering signal into different signals. One is the unwanted and one the blocking. I will not enter into details, but we will use only this one, the unwanted, which is more or less on the same level of this one here, about minus 58, 54 dBm. The blocking here has no meaning. It's minus 1000 dBm, which is meaningless. Okay, it's even not there, so it's not useful for this simulation. So these are the two signals that will be used to compute interference. These two. Okay. So here on the so we saw the outline. Then please click on the results. Here you should see something like this. Okay. Yeah. On the left side you have a summary of all your parameters on the simulation. Everything is here. Okay. On the right side you have the vectors that were generated. So if you want, please click on this one, the RSS. Set the RSS, click twice. And it should open a window. Okay, that's it. So what is that?
It's a distribution function.
Cumulative distribution function of the signal. Okay. Here you can click on the PDF. Okay. This is almost a perfect Gaussian with one dB standard deviation. You can see here the value of the standard deviation here. It's here. The mean power is minus 57 dBm. So this is the power that the receiver is actually receiving. Okay. So this is the more or less the property of the signal. You can also see the vector during time. So, okay, this is what was generated. 20,000 points, they are all there. Okay? So SEAMCAT will generate the signal as it is here. So non-modulation is defined. This is not necessary. We will use only power. Okay? So here there is no phase. The phase doesn't enter into account, at least on this section. Okay. Well, following on the next step, we have the interference calculation. Please click on it. Okay, it's completely empty. And here we'll start by computing what is the real probability of interference between these two systems. So here down, on the downside, we have here compatibility, which is the method that will give us one value, just one, between with this criteria. C over I, what does it mean? C means carrier, and I means interference. Okay, so this is a ratio, C over I, that has to be predefined It was predefined previously, I forgot to mention it. But it is predefined and the value is here. How much is it? Can you see it? 19 CP. So it means that the criteria is the following. If the difference between the signal and the wanted signal and the interfering signal is higher than 19 dBs, that's okay. It's not considered interference. If the ratio is lower, then we'll consider it as one interference event. On the 20,000 simulations, we will do this 20,000 times. Okay, and at the end, this is a very simple probability division. Number of interference events divided by the total number of events. And it will give you a probability. Okay? Okay. This is actually how SEAMCAT is computing interference. Okay, then you can just check here unwanted. Okay, just please check that this is actually unwanted and not blocking. And then you can click on the calculate. Okay, what is more important is to check this window here called results. So how much is the probability of interference?
1.
1, which means
100.
100%. Okay? Okay, so it means that both systems will interfere always. Always interfere. Okay? This is normal because we are using the same frequency. They are more or less 1 kilometer apart. And one transmitter is 30 dBm, so it's a lot. With free space, there are no obstacles. So actually they are looking to each other. So the receiver will be receiving signal from the wanted transmitter, but also from the other one. Okay. It's like hearing FM radio from two stations at the same time. This is what is happening. Okay. So is it good? Is it okay? Okay. So now on the regulator side, now they have to decide, okay, the maximum interference is 1% or 0.1%. They have to define this because it's impossible to be 0. It's impossible. So the regulators have to define this. Okay, our criteria is maximum 0.1%. So we have to check what can be done in order to have this value. Okay, here on SEAMCAT we can do this very easily by changing now. Here you can change from compatibility to translation. Okay, it is done. Now you have to come here. You have here a window called translation parameters. You select here on this upper button interfering transmitted power. Click on it to select it. And here we will define the range of the interfering transmitted power. Right now it's between 0 and 100 dBm. Okay. Someone remembers what was the value that we used on the simulation? It was 30. So with 30 dBm, I'm already 100% of interference. So I really don't need to go up to 100. It's not useful. So you can decrease this 100 to 30. Okay, that's more than enough because I know that at least at 30 dBm I already have a full interference. So I don't need to go up. The number of points for the simulation is 100. That's okay. And then you can click on calculate. Okay, you will have another results, which is here. So what you can see here on the horizontal scale, what is there? Between 0 and 30. This is the transmitted power in dBm. And on the vertical side you have the probability of interference. Where is 0.1%? Or probably it's easier. 1%. Where is 1%? Is it visible? No, it's not visible. This goes up to 100%, so here is 10%. So 1% is somewhere here, okay? So for that I can check, okay, maybe I will do another simulation between 0 and 5%, and 5% corresponds to approximately, okay, let's say 15 dBm. So I will do once more another simulation, but instead of going up to 30, I will go up to 15. And you can compute once again. So another results, and probably here it will be easier to check. So now where is 1%? Can you see it? 1%? So here is 5%, 4%, 3%, 2, 1. So to have an interference probability of 1%, what should be the power? You can check here, it's around 13.5 dBm. So here you could give an answer to the regulator saying, okay, in order to have an interference of 1%, the interfering transmitter should decrease its power from 30 dBm to 30 to 13. Okay? This is the only way. So, okay, and that's it.
It's too much.
So, yes, so probably it will have, I think the better idea is to change frequency, not to decrease power, otherwise it will not be useful. Okay? Okay, this is a very simple example, but this is to understand how SEAMCAT works. This is mostly parameterization. This is a very tricky exercise at the beginning because you have to check the consistency of the system. Okay? Very good. I have still time? Yes. So we will run now the second exercise. Okay? But we'll see that this is a little bit more complicated. Anyway, no problem. So please click here on the open. You should have already access to the second exercise. You just have to click on it, wait a little bit, and it will open this second exercise. Okay, in my case it opened in the layout system. I will click once again on the, for example, on the receiver. So, this second exercise, maybe to explain it, I will open here the guide, the support document. You already have this document in the share folder. So we'll go down, because here it's the first exercise. Okay, the second exercise starts at page 8. Page 8. How do I increase this?
Yeah, plus.
Okay, this second exercise is modeling interference between mobile systems. Okay, and now the scenario is completely different. Now we have mobility, and we have to define more or less this scenario here. So here what we have, so we'll describe a scenario of interference into a base station of a multi-channel mobile system from one mobile station of another mobile system. So the idea is to, so we have here this base station, and in that case we will use only the receiving side, so we'll be analyzing the uplink, not the downlink, just the uplink. Okay, and in that case we'll see what is the interference caused by this mobile transmitter here on the other cell. Okay, so obviously we'll define certain parameters that may allow for this scenario. So first of all, the base stations are fixed. But around the base stations we'll define a circle. You can see this is a coverage area of the base station where we'll put some mobile transmitters that will be moving along the simulation. So they will be farther or low or high or higher distance relative with this receiver here. So this will be our victim here. So this will be our victim, and here it will be our interferer. Okay. So obviously we have to define a lot of parameters. I will skip a little bit this, but the height of the antenna, the power, everything. And very important, since this is a mobile system, we'll define a frequency hopping pattern for the victim link. You know that in the mobile operators, each base station has a lot of channels available, 4, 5, 6, I don't know how much. And here we'll define that on the victim cell, we'll have 5 available frequencies. 5. Okay? So the interferer will be using one of them, just one. Okay? So it means that from time to time we'll have interference, because this is a co-channel interference. So it will interfere on the victim system, but not always, okay? Because the frequency will be changing along the simulation. So in SEAMCAT, how do we define this? Well, through what we call user-defined stair. Okay? So what we define here? Central frequency of the channels. How many channels are here? 5. Okay. And for each we define a cumulative probability. In that case, for this channel 450, the cumulative probability is 0.2. So it means that 20% of the time this will be the channel in use. Okay. Next channel will do exactly the same, also with 20%. But we have to, since this is a cumulative probability, we have to add the previous one. So here, for this channel here, 125 kilohertz ahead, we have a cumulative probability of 0.4, and so on. So we'll define at the end, so all these channels will be used with the same probability, 20%. Okay? For Bluetooth, you should do this 80 times, I think. These are 80 channels. Okay? With the same probability. My suggestion is, if you want to do this, please use an Excel file where you define the frequency and the probability density. Create it on the Excel because it's very useful. Copy the results in a text file, and then import this text file into SEAMCAT. Please don't do this here because it will take 1 hour, and you can have wrong results at the end. Okay, and Excel is very useful. Okay, so going ahead, so here are some results. So probably I will show this on the simulation side. Then we'll try to understand what was the results. So please go back to SEAMCAT. So I will go immediately to the scenario. Okay. I will just check if everything is okay. And yes, everything is okay. By the way, here the propagation models are extended data, so it's no longer free space. Okay. Extended data is a version of the optimal data, but for extended frequencies. Okay, because the original was not for this kind of frequency range between 30 MHz and 3 GHz. Okay, anyway, checked everything, so please run the simulation. Okay, now I will zoom it. So I think it's this one, right? Okay, but it's not needed because actually we have all the systems here. So I'm trying to see if I can see the green victim link transmitter. Probably it should be but okay, no problem. So, but by the way, here you can see that we have actually both systems. Victim receiver, victim link transmitter are located in this side, and then we have the interferer transmitter in red, the interfering receiver in yellow, which is more or less here. Although they are correlated between them, but then the distance to these points here can change. So, results. we have here, you can check here. So the desired signal, you can click it once and see that this is actually a common signal. Okay. Although it's not completely symmetric, it's not. We have a little bit of, this is due to the propagation model that we use and some other parameters, but this is not free space anymore. And the interfering signal, RSS, is no longer uniform. You can click on the PDF here. Well, what is happening here? So because probably you were not expecting this on the interference signal, but because here you have the probability of density function of this signal. We'll see the explanation, but we can see that here we have higher power on this section here, and here much lower power. We'll check this later. Here we can then go on the interference calculation, and I will not change anything, I will just compute and see here. So how much is the probability of interference in this scenario? 17%. Okay. In this particular scenario, obviously, we could change a little bit of these parameters. So the explanation for this scenario here. Okay, we have here co-channel interference. Changing the scenario, so the frequency of the frequency moved to the next adjacent channel. This will all reducing the probability of interference below 1%. It means that, okay, in that situation, we should at least remove this specific channel that is the same as the adjacent cell in order to avoid interference, which is what all mobile operators usually do. Okay, they do not use the same frequencies on adjacent channels, and not also on the same channel, the same cell. Otherwise, they will interfere with themselves. Okay, so this was my presentation on the SEAMCAT. I know it was quite short, but at least you have a little flavor of the SEAMCAT if you want to use it for later use or for other works, you can obviously use it. Okay? So my contacts are also with your teacher. So whenever you want to contact me, you can send me an email. Unfortunately, I will not be here tomorrow. I have to leave to Carlo, but I wish you a lot of success. Okay? So thank you for attention.
Thank you.
Thank you.